Hello everyone. So in this free lecture tutorial I wanted to supplement what I had discussed in the previous free lecture tutorial related to calorimetry. And in the examples that I gave in the previous tutorial, basically we had chemical components mixing, we were neutralizing acids and bases in one example, and we were combusting a sample when we were talking about bomb calorimetry. And so each of those represents a chemical reaction taking place, but I wanted to underscore that calorimetry principles don't just apply to chemical changes, they also can apply to physical changes. And so in those instances where we have a component of our system changing state, perhaps from solid to liquid or from liquid to gas, then we have to account for that change as well. We have to account for the energy that is spent actually getting that component to change state. And so one way that we can actually monitor this is to actually examine what we call heating and cooling curves. And so I've included an example of a heating and cooling curve in this particular slide. And if you take a look at it, basically let's begin all the way down here on the left. At this point we have ice at negative 20 degrees Celsius. And so we're going to heat this ice until it reaches 0 degrees Celsius. And so much like we learned in the previous pre-lecture tutorial, if I wanted to calculate the heat that I need to invest to heat the ice from negative 20 degrees Celsius to 0 degrees Celsius, then I would use the formula where the heat is equal to the mass of the ice times the heat capacity or the specific heat, depending on whether we're dealing with a quantity of ice in moles or a quantity of ice in grams. But some representation of the heat responsiveness of the ice times the change in temperature. Now obviously we know that at 0 degrees Celsius ice melts, but during a phase change temperature does not change. So if you notice, that portion of the heating curve for this ice has gone completely horizontal, because for as long as there is ice within my system instead of liquid water, the temperature will not change. It's only when all of the ice has been converted to liquid water that the temperature will begin to change again. And so simply applying the formula that I did as I was heating the ice is not going to give me any sort of quantitative estimation of the heat required to actually melt the ice. Instead, what I need to do is I need to take a quantity called the enthalpy of fusion, and sometimes these are given as molar quantities, so heat of fusion per mole, and I would need to multiply that times the number of moles of ice that I have in this particular sample. And so that would actually tell me how much energy is put in to melting the ice. Now once again, once I have water, then I can heat that water. And as we know, I can heat that water until I get to 100 degrees Celsius. Now again, in this portion of the heating curve, basically I can calculate the amount of heat it would take to actually heat the water by employing, again, the relationship that the mass of water times the heat capacity of the water times the temperature change would give me a quantitative value for the heat that I actually just spent heating that water from 0 to, say, 100 degrees Celsius. But once again, once we reach 100 degrees Celsius, then once again the heating curve goes flat. Okay, because at this point water begins to vaporize. And similarly, in this particular case, if I want to calculate how much energy must be spent to actually vaporize this sample of water, I would need what I call the enthalpy of vaporization, or the heat of vaporization. Again, these are often given as molar values, so per mole, times the number of moles of water I have in this sample. And then suppose that once I've actually fully converted my entire sample of water to steam, suppose I wanted to heat the steam further. I could if I chose to. Then basically then the heating curve would continue to produce a temperature change within the steam if I continue to heat it. Now basically here in this region of the curve, once again, if I wanted to actually calculate how much energy is necessary to heat this sample of steam to a certain temperature, then basically I would need to, once again, multiply the mass of steam that I have present times the heat capacity of the steam multiplied by the temperature change that represents my final and initial temperatures of the steam. And so it is entirely possible, based on this approach, for me to actually calculate how much energy is needed to, say, take a sample of ice from negative 20 degrees Celsius and melt it until I have water, and then heat that water to a specific temperature. Now, the other point I want to make regarding these curves is, again, notice that these are called heating and cooling curves, because I could just as easily read this curve from right to left instead, in which case all of these different heats that I'm calculating would all become negative values, because basically that energy would be lost by the system and transferred to the surroundings. In the case where I'm reading the heating curve from left to right, basically I'm putting energy into the system to provoke all those changes, so basically each of these terms would then be considered positive value, since again it represents an investment of energy into the system. So let's take an example problem. Okay, I'm being asked to calculate how much energy is required to heat 25 grams of ice at negative 25 degrees Celsius to water at 95 degrees Celsius. And I'm given the heat capacity of ice, the heat of fusion of ice, and the heat capacity of water. And so let's think about this for a minute. I'm just going to map it out in words first and then construct my terms after. First I have to heat the ice from negative 25 degrees Celsius to 0 degrees Celsius. Then I need to actually melt the ice, so I convert the ice to water. Okay, and then once I have the water, I'm going to heat the water from 0 degrees Celsius to 95 degrees Celsius. Now I'm going to construct terms for each of those processes. If I'm going to heat ice from negative 25 degrees Celsius to 0 degrees Celsius, then that should be my mass of ice times my heat capacity. In this case, they gave us a specific heat capacity. Notice this is not a molar quantity. So I need the specific heat of ice times the temperature change between 0 degrees Celsius and negative 25 degrees Celsius. Okay, so that's one term. Then I need to melt the ice. Well, that involves the heat of fusion. And so in this particular case, even though heats of fusion can be given as molar quantities, in this case they gave it to me as a specific heat of fusion, since it's in units of joules per gram. So basically that means I need the heat of fusion times the mass of the ice that I'm going to be melting. And if I do that, I should get an expression of the amount of energy necessary to melt that ice. And then lastly, I have to heat the water from 0 degrees Celsius to 95 degrees Celsius. So again here, that would be the mass of the water times the specific heat capacity of the water times the temperature change. Okay? So now that I have my terms all mapped out, let me go ahead and substitute in. We said they were 25 grams of ice, and the specific heat capacity of ice is 2.077 joules per gram times degrees Celsius, and the temperature difference between negative 25 and 0 is 25 degrees Celsius. Then I'm going to add the heat of fusion for ice, so that's 333 joules per gram, and I'm going to multiply that by my mass of ice, which is 25 grams. Then, my last term, I'm going to take my mass of what is now water, which is 25 grams, and then I'm going to multiply that by the specific heat capacity of water, which is 4.184 joules per gram times degrees Celsius, and then I'm going to multiply by the temperature difference. Well, I'm going from 0 to 95 degrees Celsius, so then that should be a temperature difference of 95 degrees Celsius. So if I go ahead and do the math, notice that my units cancel, so that basically I'm only left with units of joules. When I do the summation of all of my terms, if I go ahead and do this math, I end up with 1.96 times 10 to the fourth joules to actually take 25 grams of ice and heat it so that it goes from ice at negative 25 degrees Celsius to water at 95 degrees Celsius. So go ahead and work on the follow-up assignment. I've given you a similar problem to work on. We'll continue to go through some additional principles of calorimetry and also some additional exercises. If there are any questions, again, by all means, email, or if not, we'll speak in class tomorrow. Have a good night.